Hello everyone, and welcome to this Smithers Rapra, VICTREX and Magma webinar, Durability of PEEK Polymers in Thermoplastic Composite Pipes for Subsea Oil and Gas Applications. My name is Dan Rogers. I'm your moderator today. For those of you who don't know me, I'm Head of Publishing at Smithers Rapra, which delivers industry-leading rubber and plastics expertise from product concept to launch and beyond. Before I hand over to our speakers, Jeff Small and Mick Mullen, just a few brief words on the logistics of today's event. Proceedings will be emailed as a PDF shortly after the event. The file will contain a link to the full recorded version of the presentation, which you can access on demand. Following the presentation, we will use any remaining time to host a question and answer session lasting around 15 minutes. Please use the Q&A box on the right-hand side of your screen to send us your questions at any time during the presentation, and we'll go through as many as we can at the end. During the presentation, there will be chances for you to get involved by taking part in our industry polling. Our presenters will be pausing a couple of times during the session and will introduce a polling question. Simply click on your choice of response in the polling box on your WebEx screen and hit Submit. Immediately after, we'll share the results and some analysis. Finally, should you encounter any technical issues, please use the chat feature to notify us. If you have any audio issues, we recommend closing larger programs like Outlook, Lotus, or iTunes. And so to the presentation. It is my pleasure to introduce our speakers today, Jeff Small and Mick Mullen. Jeff Small is Market Technology Manager for Energy at VICTREX. Joining Jeff today is Mick Mullen, Analysis Manager at Magma Global. Magma produces M-Pipe, fully bonded carbon composite pipe. Magma's mission is to deliver the world's most reliable risers, jumpers, and intervention lines for subsea use. Jeff, with that, over to you.
Thank you very much, Dan. Good afternoon, good morning, and possibly good evening to everybody who's kindly joined the webinar. We'll be talking about PEEK in the Magma M-Pipe in this presentation. But I wanted to start off with a few slides about VICTREX PEEK in oil and gas in general. Now, PEEK, as I'm sure you're aware, has been around in the industry for at least 30 years, coming up 35 years in some applications. The polymer is almost certainly known to a lot of you who are attending the webinar. And if you know even just a little about polymer, you'll know that it's well known for properties such as high strength over a wide range of temperatures, very good creep resistance, and resistance to aggressive chemicals and so on. So you can see how it lends itself to some of those applications which are up on the screen right now. Now, in addition to applications like seal rings, for example, which really rely on properties like very high creep resistance and very high chemical resistance, there are also a range of applications which rely on a different set of kind of unique combination of properties, and those focus more upon toughness and fatigue resistance. And so I've popped up a couple on the screen there. One is compressor components, which obviously see very high fatigue loadings, and another one is wire and cable insulation. So these are applications which people are generally fairly familiar with for PEEK polymer. Now, moving on to the current innovations, as it were. With the 30-odd years of history in this field, I suppose it's not surprising that people recognize PEEK more for its applications in things like seals and backup rings than in some of these newer areas. And specifically here, I'm talking about pipes, VICTREX pipes. We have a business which manufactures high performance, high quality pipes in diameters from quarter to around 8 inches, and in lengths at least up to a few thousand meters of continuous length. So that's quite a new development. And of course, as many of you will have seen fairly recently, we are now a manufacturer of high performance composites, continuous fiber reinforced composites. again finding applications in a wide range of industries. And for the subject of today's presentation, both of these product forms from VICTREX are brought together in Magma's M-pipe, Thermoplastic Composite Pipe, TCP. So for the next short section, I'd like to talk a little bit about thermoplastic composite pipes, which are known by their acronym TCP. These are described in a recently finalized document by DNV GL. It's a recommended practice, F119. And that recommended practice describes the parts, the component parts, the function, the design, the testing, and the qualification of a TCP. It's set out all in that document, and it is downloadable from the DNV site. Now, the DNV document describes basically a pipe precursor for a thermoplastic composite pipe. This is the inner part of the construction, and it bears actually no significant part in the overall strength of the pipe itself. Its main function is to act as a chemically and permeation resistant barrier. Ideally, it will have a very smooth surface and provide improved flow characteristics for the diameter of the pipe. And of course, it should be wear and erosion resistant, because you want that smooth surface to remain for as long as possible. The design code is quite explicit in how liner materials need to be tested. And specifically, it requires that the liner must have proven operational capability at the maximum operating temperature. Excuse me. Then there is the pipe body laminate. That is the kind of the guts of the construction. The pipe body laminate provides all of the strength and pressure capacity of the thermoplastic composite pipe. Obviously, the mechanical properties of composites are dominated by your fiber choice. First and foremost, if you have a carbon fiber composite, that is going to dominate the properties. But also the quality of the polymer fiber interface. That fiber matrix interface is extremely important, and we'll say a little bit more about that in a few minutes' time. The other point to note in thinking about a TCP construction is that continuous fiber reinforced composites, carbon fiber reinforced composites, would typically be working at a maximum design strain of significantly less than 5%, probably more like 2 to 3%. So the reasons for mentioning that will become clear a little later in the presentation. So then, VICTREX PEEK polymer then is a critical component, an extremely important component of M-pipe. It forms the chemical permeation resistant internal barrier, but it also holds those carbon fibers which are providing all of the strength and collapse resistance. It holds all those together as a very tough and chemically resistant matrix. So that PEEK is clearly very important in both roles. So now we'll look in a little bit more detail at the pipe precursor. Now, in terms of pipes in general, what we've labelled here is the familiar. Early thermoplastic pipes, so they still exist clearly, typically used for things like gas and water transportation, and everybody, I'm sure, on the webinar has seen plenty of pipes by the side of the street, which look just like the ones on your screen now. These typically would use polyethylene or polypropylene as the material. So when the oil industry began to move towards higher performance materials, needing pipes and tubes of higher thermal and chemical resistance, it was a natural progression to move to extruding continuous pipes in materials like nylon 11 and 12 and of course PVDF. That was just a kind of a logical extension, really, of the use of polyethylene and polypropylene. So, in something of a departure from the norm for VICTREX PEEK, some years ago we invested quite significantly in developing both materials and process technology to be able to extrude continuous lengths of PEEK pipe. And these are obviously very, very high performance materials, and being as PEEK has such exceptional chemical and temperature resistance, a PEEK pipe is going to excel in being able to carry all oil industry fluids, ranging from hydrocarbons, water and gases, which range from sort of rather passive things like CO2 in the case of polymers, to very highly aggressive gases like H2S. So we have, as I say, we have now a capacity of manufacturing and spooling pipes in continuous lengths, and you'll see one on the right-hand side of the screen there. It's, excuse me, that is a 3-inch diameter pipe. And as you see, the material is clearly nicely ductile. It spools quite nicely on and off, and is handled by Magma accordingly. I just wanted to share with you a brief video clip, which for the sake of time, I will probably accelerate at some point. This is a crush test on a 3-inch PEEK pipe. And we've made it extra tough on the PEEK because we're running this at -60 centigrade. So this is a particularly difficult test for material to get through, and it's really demonstrating the ductility of the PEEK pipe. And this kind of test is one which we employ to demonstrate clearly that we are manufacturing pipes of the required ductility for the application. And if I just accelerate this a little bit for you, you'll see that as the pipe is compressed at a fairly fast rate, we reach a point where, in fact, the both opposing faces actually come to touch, and there will, of course, be some yielding at the edges. But when the load is released, you'll see that the pipe recovers quite substantially and demonstrates quite nicely the ductility of the pipe as it's extruded. Now, on the subject of toughness of the pipe, as an industry, I think we've tended to talk about toughness of materials in quite often in fairly vague terms. You'll often hear people talking about impact strengths that tested to various standards. Elongation at break is another thing which is talked about, and none of these really give us a very clear picture of how the polymer is going to perform in an application. Now, in material science, as I'm sure many of you will know, that there is a quantity referred to as the fracture toughness, a measurement you can make. It's a far more definitive and pragmatic way of comparing materials. It's an inherent property, just like tensile strength or tensile modulus, and it tells us a lot more about the ability of a material to resist the propagation of a pre-existing flaw. So it assumes, for example, that all these materials have got the same flaw, and it's a measurement of how well that they resist that flaw propagating and freely accelerating as a crack. This chart is something I've pulled together from searching on the internet, and it's simply to sort of demonstrate really that there is quite a range of fracture toughness as you look between different polymers. But PEEK, according to my survey of the available data, is right up there. Depending on the grade and so on, is right up there among the tougher of the materials. And you'll see even the PEEK composite, actually, the PEEK carbon fiber composite has fairly high levels of toughness. what I had wanted to do in this slide was put some kind of parameters around PEEK and other commonly used pipe materials which are used in the industry. However, it is particularly difficult to find that data on the internet. So we've recently run some testing of our own single edge notch bending fracture toughness. Single edge notch beam fracture toughness testing. And you'll see here we've compared VICTREX PEEK polymer nylon 12 and the PVDF polymer, and you'll see that actually there's not a huge amount between them, but in fact the PEEK polymer is in fact the toughest of the three. So PEEK is clearly very well suited as a pipe precursor. It has a very high resistance to crack propagation. Now, moving on to the composite laminate. As with the PEEK polymer, PEEK-based composites have a very long and extremely well documented history. I think, to be honest, that PEEK is probably one of the most documented composites in the whole of the materials world. It was developed back in 1981, mainly as an aerospace material, but since then it's been extended into medical applications, things like trauma plates, which require very high fatigue resistance, loaded brackets for, as you can see in this picture, for aircraft parts, which are again critical parts and need very high fatigue resistance. And in the energy industry, there are already applications in areas such as wear rings and compressor parts. So this material is of course very well known for its high strength and stiffness. It's got an extremely good fiber matrix interface, which we'll talk about in just a moment. And of course, being built around PEEK polymer, it's got great chemical resistance. The toughness and the fatigue performance are a sum of the materials of construction, and also the interface between the fiber and the matrix. And as I say, excuse me, if you make the simplest of searches on Google or any other search engine around PEEK composites, you'll be pleasantly surprised, I think, by the wealth of data that has been published on this material. So we're not talking about a super new material. We're talking about a very high performance material developed for the aerospace industry, and now finding application in a very high performance composite pipe. Now, one of the reasons that there is such a good interface between PEEK and the carbon fiber is that they are very compatible on a molecular level. So you'll see here a very rough kind of sketch of a graphite structure, and here we have a repeat unit of a PEEK molecule. And you'll see that the two superimpose upon each other quite nicely, in fact. The reference for this is at the bottom of the bottom of your screen. You'll be able to pick that up if you download the presentation later. Now, it is an approximation because of the form of the molecule being three-dimensional, but it does demonstrate clearly the close compatibility of these two materials, and it's known to be associated with enhancing crystallinity around the fibers and so on. So clearly these two materials are very compatible, but it also needs saying that a good composite is also very largely due to the way that it's manufactured, and you need excellent fiber wetting, very low void content, and so on. So with PEEK, we have with PEEK matrices at least, we have a very high performance interface between the two constituent materials. So, with that said about PEEK, moving on now to materials selection. So, how do you go about selecting materials to manufacture a thermoplastic composite pipe from? Now, firstly, I've put up a slide here which is comparing some mechanical and thermal properties, and I've picked out PEEK, of course. a couple of nylons, 11 and 12, which are used for flexible pipes. Those are flexible pipe grades, PVDF flexible pipe grade, and a HDPE pipe grade. Now, this isn't to say that any one material is ideal for any particular application. This is very much a case of you choose the appropriate material for your application. And there will be applications where clearly something like a HDPE will be more than adequate. I think the key takeaways is really that the PEEK material is very high strength, as you can see, something like 3 times higher tensile strength than the next nearest material. It is of course stiffer, but in a composite at least, that extra stiffness is dwarfed by the stiffness of the carbon fiber, which is a common feature in all of the polymers you can see. Strain at break in all cases greater than at least 50%, and depending on what you're comparing with, density, there's not a lot in it really between all the materials. The really key difference you can see from the chart on the right-hand side of the screen. So PEEK has a long-term service temperature, which is around the same order of magnitude as the melting point of the other 3 materials. So you have a material in PEEK which will offer a great combination of mechanical properties, but it will retain those properties over a very wide temperature range, which would potentially give you much greater confidence in operating a PEEK composite pipe, perhaps at temperatures towards the peak of towards the top end of the operational temperatures of those other polymers. Having said that, as I say, keeping a completely independent hat on, there will be applications, lower temperature applications, where those other polymers may well be adequate. Excuse me. So when you're selecting your liner and your matrix, your mechanical properties really relate to having a pipe which can be readily handled and can be used as a precursor for the full composite. The actual mechanical properties then almost fade to insignificance because of the composite which is put on the outside. What is important about the liner, the precursor, is that it has excellent chemical resistance. This is probably the most important function of the liner. So here I've basically set out 6 sort of broad brackets of chemicals, and I'm comparing the polymers that we've just been looking at in terms of mechanical properties. I'm just comparing their chemical resistance. I guess firstly the key thing to notice is that PEEK, and I'm sure you're aware of this because, as I said earlier, it's been around 30 years or more, has exceptionally good chemical resistance across the board, really, right from highly sour fluids right through to acids and so on. So really good chemical resistance, and there isn't a solvent for PEEK below 200 Celsius. So it retains that chemical resistance over a very wide range of temperature. As I say, these other materials all have fairly promising chemical resistance at room temperature, at ambient temperatures, but of course they are limited. I've taken this data from a number of sources which you can look at your leisure, but you'll see that, for example, the nylons, that their chemical resistance is beginning to reach its limits when you get up to around 60 degrees centigrade. That's where you really have to think carefully about the chemicals you're putting down the pipe. Even with excuse me, even with PVDF, which has improved thermal and chemical properties, really by the time you get up to around 100 degrees centigrade, that's probably about where the chemical resistance begins to bottom out for that material. And remember that that material in particular will melt at around 165. So you know, as soon as you're getting up towards that melting point, you would expect your chemical resistance to be dropping off. So long-term chemical resistance, and by that I mean many, many thousands of hours of test data to support it, PEEK really does excel in that area. And of course, it's not just all about just pure chemical resistance. Permeation resistance here, we're excuse me, we're talking about H2S permeation. And I just draw your attention then to the to a few numbers around the center of this table. PEEK is generally something between 30 and 100 times better than the next best competitor, and we have measured that not only for H2S but also for methanol permeation. Also, of course, lower permeation means slower degradation of the properties in your composite, because aggressive chemicals are permeating much more slowly. But also, it means a lower susceptibility to rapid gas decompression. The fluids and gases find it much more difficult to travel through a PEEK barrier. Permeation is also quite uniquely, I think, in PEEK, is unaffected by saturation with hydrocarbons. So if your pipe precursor is fully saturated after many years of service with a hydrocarbon, it won't affect the rate of permeation through. There won't be a sudden onset of additional permeation. So here I just wanted to focus really on what dominates the performance of the final M pipe itself. And I know Mick will talk more to properties of M pipe a little bit later. But if you consider a 55% volume fraction carbon unidirectional composite, then most people will know the rule of mixtures for composites. But basically, what this means is that the carbon fibers themselves will dominate the properties of the composite, and that if you look at the modulus of any 55% carbon reinforced polymer at ambient temperature and with the same layup, then the stiffness is only going to vary by about 2%. So under ambient conditions, you would expect to see extremely similar performance in all of those composite materials. Where things do begin to differ then is where we're talking about the strength of the material rather than its stiffness. And strength is very strongly related not only to the strength of the matrix itself and the fibers, but the fiber matrix interface. So as I pointed out a little earlier, PEEK has a very unique fiber matrix interface, and I think it probably is unique amongst all of those other composite options you can see there. Also, of course, the strength depends on the composite quality. You want to ensure that the quality of the PEEK composite you're receiving is high enough to manufacture what you need. Most importantly, again here, the environmental factors on the composite. So although the fibers are dominating the performance, elevating the temperature, raising the temperature, making the chemical environment more aggressive, all of these things will attack the matrix material, and as that degrades, then obviously the composites of the properties of the composite will decrease. So if you have a significantly more chemically and thermally resistant matrix, you will have a significantly better performing composite. So although all of these materials appear to have very similar properties at the outset, once you start talking about environments and temperatures, you see quite a different picture. So piecing these various thoughts together, I think these are the properties of PEEK which are relevant to the two basic components, the composite and the pipe precursor. There are some, in fact many of them are common to both components, chemical resistance, thermal resistance. But the point I wanted to convey most importantly here is that both materials are very well established. They've both been around for 35 years or more. They're both incredibly well documented. There's a lot of data. a lot of supporting data and a lot of experience with their use. And finally, before I think we may have a polling question, certainly I wanted to talk a little bit more just about the final quality of toughness of the finished item. It's more than a combination of the two materials, the PEEK and the carbon fiber. It clearly comes down to the manufacturing and the exhaustive testing, which is carried out on materials which have been made. There's probably sufficient information really for another webinar alone on testing and qualifying of M-pipe. Certainly Magma have conducted many thousands of tests and achieved outstanding fatigue performance and pressure performance. And in fact, we will, as a joint effort again, be discussing the whole qualification of M-pipe at some upcoming conferences in both the USA and Europe this year. But before I hand over to Dan for a polling question and then over to Mick, I just wanted to share this is slightly indulgent, but this is my favorite video clip of the testing of one of Magma's 6-inch M-pipe. So this is a full-scale pressure and bend test. So you can see there that the pipe is being bent in stages. And the video continues. And then I'll just accelerate it on a little bit, and then we flex back. So I think it's when you actually handle these materials, you may question how flexible they are. I think there you have a great, very tangible picture of just how these materials will behave in bending. So, Dan, I think this is your good self.
Great, thank you, Jeff. So this is now your chance to get involved, and as mentioned at the start of the webinar, we're looking for you to get involved in the polling questions. You'll see the options for today's first polling question appearing on the right-hand side of your screen right now. And as you can see on the slide there, we have the question itself: which performance benefit of PEEK composite pipe do you think is the most important? And we've got a few key options there for you. So a lightweight pipe, high temperature capability, high pressure capability, high flow rate, sour service, corrosion resistance, fatigue resistance, or collapse resistance. And I can see that we're starting to get some of the answers from today's attendees already. Jeff, we've heard a fair bit about this, about the topic of PEEK composite pipe so far. Why was this an important question for you? And is it to a certain extent related to specific applications, or do you think there's going to be some overarching values in terms of importance here?
Thank you. Yeah, I think we're interested in this this particular question very much from a polymer point of view, in understanding which aspects of the polymer performance are most important to the people who have dialed into the webinar. So we talk, as I have today, about the high temperature capability and the chemical resistance to sour service, and clearly we think that those are very important qualities, but it's very important to understand what people out there in the industry are actually thinking. So yeah, I shall be extremely interested to see the results from this first poll question.
Great, thank you very much, Jeff. And we have just, as you can see on the screen, a few more seconds for people to give their results, and then we'll take a quick look at the results from that. Okay, so now if we take a look at the results, and in the polling box on the right-hand side of your screen, you can see there the responses. We have the individual responses and then the bar graph, and it looks like high temperature capability features very highly in terms of responses, and also fatigue resistance in a very close second there. Is that what the kind of thing you expect to see, Jeff?
Well, actually, yes, that's both what I expected. I think high temperature resistance I was expecting to be important. It's very interesting to see that fatigue is an important parameter, actually. I mean, we believe it is, but that kind of confirmation. If I'm honest, I thought possibly corrosion resistance might also be somewhat higher, but that's extremely useful information.
Yeah, well, certainly corrosion resistance is in there as one of the more kind of secondary factors alongside lightweight pipe and collapse resistance. But yeah, interesting results. Thank you very much.
Thank you. So at this point, I'd like to pass over the mantle to Mick, who's going to go into more detail now about M-pipe.
Good afternoon, everybody, and thank you for dialing in today. Before I start, I'd like to thank Jeff for a very comprehensive presentation. I think he's given us a very clear view on the attributes of PEEK, the many attributes of PEEK, and its application and its history within the industry. So building on that today, I'd like to take a few slides just to explain to you in a little bit more detail about a more specific application of PEEK in M-pipe itself. So I'd like to talk a little bit about what is M-pipe, how we design M-pipe, the materials that we use for that, and also give you a view on where it sits in the market and where we are in terms of our progress in developing the product. So I guess first of all, an introduction to M-pipe itself and what is M-pipe. So M-pipe is a high quality, high strength, flexible thermoplastic composite pipe. So essentially the construction of the M-pipe means that it's a monolithic structure from the bore to the surface of the pipe. M-pipe as a system consists of two individual subsystems. There's the pipe body itself, so the composite pipe body, and then the end fittings. And the end fittings are used to connect M-pipe to interface M-pipe with other equipment in the field. The two subsystems are designed and manufactured separately. So here at our factory, we manufacture M-pipe to the required length, and then we terminate the pipe with an end fitting in order that it can interface with other equipment. So some more details then on the pipe body itself. M-pipe pipe body is manufactured from two precursors. The first precursor is the pipe precursor itself, which is extruded from VICTREX PEEK. Then the laminate itself is built from a carbon fiber PEEK tape precursor. So this tape, which uses Toray T700 impregnated with PEEK, is used to build up the laminate. We believe that PEEK offers the best performance available across a range of polymers, as Jeff has already pointed out. And in selecting our fiber, we chose Toray T700 because we believe that offers the best characteristics for the requirements of a TCP, thermoplastic composite pipe. As Jeff has already touched on, it's not only the high performance of these two individual materials themselves that deliver the performance of M-pipe, but it's the combination of them, the selection and combination of these two materials, and the good quality match between the two materials that actually adds synergy to that combination and gives us an enhanced performance, which we believe sets M-pipe as best in class in its field. During the manufacturing process, the pipe precursor is used as a manufacturing mandrel, so that's the start of the process. As we go through manufacture, we build up on that pipe precursor, and through a 3D welding laser printing process, we build up the laminate layer by layer in order to achieve the structural laminate that does the load carrying job on end pipe. So the pipe precursor itself, as Jess says, is really there for as a fluid conduit, and the structure is achieved through the laminate. So the two are fully bonded together, which means we have a fully bonded product from the bore of the pipe out to the outer surface of the pipe. And the final point, of course, the material combination, we believe, delivers the best performance for a TCP. So a little bit about the design process and how did we end up there. So again, this really repeats a lot of what Jeff has said, but if we look at it from a Magma point of view, we've spent an awful long time early in our development looking at what's the best polymer for end pipe. So our approach is that we want to operate best in class. So we want our product to offer the best performance if possible across a range of TCPs. And in order to do that, we identified the best polymer we felt was suitable for that purpose. So some of the things that were important to us when we went through that long process of identifying PEEK as the most appropriate material for a high-performance thermoplastic composite pipe, we looked at its track history in the industry, and we saw that it was widely applied within the oil and gas industry. It was commonly used in applications like connectors and seals, which really proved out its excellent chemical resistance and creep characteristics. And PEEK has a proven performance in extreme oil field environments, so it's very good at dealing with source service, high temperature, and it has great fatigue and sensitivity. So all of these characteristics led us to believe that it really is a good polymer for dynamic pipe applications. So then the design of the pipe itself. So as we say, we're using PEEK carbon fiber impregnated tapes. If we look at the loading that we're going to see on a pipe, this loading comes from various scenarios. It can and it depends on what the application is. So in some applications, we're dealing mainly with pressure. In others, we want to spool the pipe. In others, we may want to carry axial loads. And so it's the combination of those loads which will really define what way we design the pipe. To manage pressure loading, we would align fibers in the hoop direction, which manage hoop stresses that we develop from pressure. And then in order to manage axial loading or a requirement for high strain in the axial direction, then we will align fibers in the axial direction according to what load we want to carry and what level of flexibility we require in the pipe. When we call them axial fibers, they're not actually aligned in the axial direction, but they are aligned in typically something like a 45-degree angle, so they work in an axial direction. So those combination of fibers define the laminate, and this laminate we've used across a series of applications, as you can see on the slide here. So where is end pipe and how does it perform and what does it cost? So end pipe is actually lower cost than other non-metallic and non-bonded flexibles of comparable spec. Now, it's quite counterintuitive to think that the best quality product will be the lowest price. But just because we employ higher quality and more expensive raw materials doesn't make the end product itself more expensive. What we find is that when you combine good quality raw materials, the final product is often better than the sum of the parts that go in, and it's often and always generally better than products developed from cheaper or lower quality raw materials. There are examples of this all over the engineering industry. I've spent a lot of time in automotive, and in recent years we see composites being adopted more and more in the automotive industry. despite the fact that it's a more expensive raw material. The fact that it can cover multiple functions mean that its introduction in applications such as bulkheads and floor panels means that it's displacing more traditional materials like aluminium and steel. So that higher quality laminate that we get with M-pipe allows us to develop pipe with a thinner wall. And that thinner wall for the same specification means that we have a cheaper product. With M-pipe, we focus on single materials, so we have carbon fiber and PEEK. Our focus on single materials means that the work that we need to do to characterize our material performance, to understand its performance in fatigue at a range of temperatures and in a range of environments, is much more focused. So we can do this quicker and we can have a much better quality data set because we have a focus on fewer materials. The fewer materials also mean that in manufacturing, we have fewer process constraints to deal with. So we're processing and setting process parameters for one set of materials, and that allows us to deliver a higher quality, more consistent product. And finally, our exclusive agreement with VICTREX means that we have a very well-controlled supply chain. So that supply chain allows us to minimize cost, because we're working directly with VICTREX, and it eliminates any cost we would have associated with having many third-party suppliers. So that's really where we are with M-pipe in the market. And then in terms of its development and the progress we've made in developing the product over the last years, M-pipe is qualified to DNV GL recommended practice F119. Magma have been working closely with DNV since 2012 to qualify our product. Historically, most of this work has been based around the operating standard C501. Whilst this standard deals with composite components, it deals generally with composite components and not specifically with thermoplastic composite pipes. Late in 2005, DNV published the recommended practice F119. This recommended practice deals specifically with thermoplastic composite pipes, the approach that should be taken to understand the performance of the pipe, the raw materials in it, and the approach that's taken to qualify that and show that it's fit for purpose. The approach laid out in this standard is what is known as a pyramid approach. So we start with characterizing the raw material, and then we work up combining this with an engineering model to understand and to correlate the engineering model through testing at representative product or mid-scale testing. And then finally, we confirm that performance through full-scale testing. The beauty of this pyramid approach is that all of the material characterization work we do at the lower levels across a range of temperatures in a range of environments, long-term and short-term loading, all of this material data can be carried forward from one program onto the next. So for a subsequent program, there's no need to repeat those lower levels of the pyramid. All we need to do is expand it if that particular product has a requirement beyond what we've qualified in the past. So applying the approach that's laid out in the recommended practice 119, through 2016, Magma have completed the qualification of a 3-inch downline. This is completely in line with the process set out in 119. So all of the learning from that project, then we carry forward to future projects. So in parallel, through 2016 and ongoing into early 2017, we're expanding that qualification basis. So we're moving from 3-inch to 6-inch. We're also expanding. We're expanding that onto qualification of a 6-inch 10 KSI jumper. This jumper is for deep sea and long-term environment, and will operate up to 120 degrees. So as we move from the 3-inch qualification project onto the 6-inch, we're expanding our qualification envelope, and we're expanding it in terms of temperature, operating environment, and geometry. As we step forward through subsequent projects, we will continue to expand that qualification environment through pressure, temperature, environment, further and further. So at the moment we have a series of ongoing projects with specific suppliers which are looking at improving and expanding that qualification basis that already exists. So I think that's probably enough from me today. So hopefully what I've managed to give you there is an understanding of M-pipe itself, what the product is, why we've chosen the raw materials that we have, because we believe that sets M-pipe as best in class. Hopefully you've got an idea of how we go about designing the product and how it works, and where that sets the product in terms of its performance in the field. And finally, hopefully an interesting overview on where we are with qualification and adoption of the product. So that's me done with M-pipe. Thanks for your time today. I think I'm back to Jeff now for a final wrap-up slide, and I look forward to your questions.
Thank you very much, Mick. So yeah, just one very brief slide to kind of close off. And I guess the main takeaways is that M-pipe is here. It's qualified to an industry recognised standard. It's qualified by and backed up by many thousands of data points, and also very long experience, more than 35 years of experience in the use of both VICTREX PEEK polymer and also PEEK composite materials. PEEK is clearly an essential part of both the liner and the composite matrix. But of course, in the composite matrix, in the composite itself, the properties are dominated by the choice of fibre. So the main takeaway, I think, is that by selecting PEEK as a polymer, by selecting M-pipe, you have the opportunity to extend the performance range significantly beyond current, more common, possibly materials. Most importantly, chemical and permeation resistance excel really with PEEK up to and actually beyond 175 centigrade. The matrix material will actually run continuously above that without significant loss of mechanical properties. So you have a very high level of security in choosing this material combination. So thank you very much for your attention. I think, Dan, we have one more poll question before we move on to the Q&A session.
Yes, that's right. Thank you very much, Jeff. So, yes, as you mentioned, we do have one more polling question for you all to get involved in. Same again, on the right-hand side of your screen, there is the polling part, and we'd like you to answer the following question, which is, which M-pipe composite pipe benefit do you think is the most critical for subsea projects? Is it low CapEx? Is it low OpEx? Pipe standardization? Local pipe supply? Or deployment using existing infrastructure? And not to predict the outcome, but any sense from you guys in terms of what's likely to be a kind of heavy feature in your personal experience?
One of the great aspects of M-pipe is its flexibility, and so what we're finding is that a lot of customers find that this flexibility makes it very easy for deployment into existing infrastructure. So we can respond very quickly. So if there's a replacement part that needs to be installed, the flexibility makes for very easy installation. The lack of metrology means that we can manufacture very quickly and deploy quickly. So that's one aspect that we find with certain customers is of interest.
Great. Well, we have a few more seconds while people wrap up their responses, and then we'll be able to take a look at the results, and then we'll be heading into our Q&A session. So if you haven't got your questions in yet, please use the Q&A box and give those to us now, and we'll fit as many as we can into the Q&A session. And so if we look at the results here in the polling section on your WebEx app, you can see there's a reasonable spread. There's a few different things featuring. Number one is low capex, followed closely by low opex, and then we do have deployment using existing infrastructure featuring quite highly as well. Is that the kind of thing that you guys expected to see from this polling question?
Yeah, I mean, I think as we established, you know, it's M-pipe is not an expensive product, so it's not surprising that those responses come through the way they have, and ease of deployment is in there also. So I think that's broadly what we would expect to see.
Great. Well, thank you everyone for participating, and thanks for your comments, Jeff and Mick. So I think we're probably just about ready to head into the Q&A session, fit some final questions in before we wrap up today. As I say, please do submit your question. We'll get through as many of them as we can using the Q&A box on the right-hand side. And maybe if we start with this one. So why do you use PEEK rather than other polymers in M-pipe?
Yeah, well, so I think we've underlined this quite well today. You know, we undertook an extensive survey of other polymers that are available. We looked at the characteristics of the polymer. We identified what was important for us to set M-pipe as really best in class in its field. So we knew that we needed to deliver very high fatigue performance. We knew we needed to deliver high operating temperatures, very high chemical resistance, wear resistance, and all of these are characteristics that we see in PEEK. And all of these characteristics were evidenced by experience in the field. So PEEK had a long-term track record in the field, and it was a well-accepted product. So it became an easy decision for us to settle on PEEK. We did look at other polymers, and we have the option to look at multiple polymers, but we really feel that it's best to focus on what we think is the best polymer to deliver the best TCP.
Great. Well, thanks for that, Nick. Another question. Can you elaborate more on the differences between PEEK carbon composites and things like PVDF or glass composites?
Yeah. So
sorry, shall I go for that? Sorry, I'll go for that one.
Yeah,
sorry,
yeah,
I'm
sure.
fighting with Mick now to answer the questions. Apologies for that. Actually, what I was going to say is that that I think could be quite a difficult one to answer or to give a lot of details on. Continuous fiber composites in PVDF, with a PVDF matrix, I think are actually quite fairly new. If you make a search, as I've done quite a few, you'll find very little relevant information or details on PVDF glass composites. Clearly the thermal properties would mean it might be better than some of the nylons, for example, but there's so little actually on the quality of the PVDF to glass matrix combination and properties that it's actually quite difficult to give a meaningful comparison, I think.
Okay, great. Thanks for that, Jeff.
Thank you.
Let's move on to the next one. We have what are the temperature limits of M-pipe?
So, like PEEK itself, the temperature performance is excellent. So we have test data showing that we have excellent pipe performance up to 150 degrees. We've even done pipe testing, creep level testing up to 180 degrees. And whilst we do see some level of knockdown, performance levels are very, very high. So normally we would be happy to set operating temperatures of the M-pipe up to about 150 degrees.
Okay, thank you for that. And just for those participating, it does look like we're going to run ever so slightly over, but I think there's so many great questions coming in that I think we should try to get through as many of these as we can today. Let's come to this one. Is there any limitation on the service environment of M-pipe, like H2S, CO2, etc.?
No, so the service environment, in terms of the chemicals that we transport with M-pipe, the limitation of that is based on the limitation of PEEK, as the fluid conduit is a PEEK fluid conduit. So in terms of media like CO2 or H2S, that's well within the capabilities of M-pipe. VICTREX have completed extensive testing and have extensive knowledge. Jeff, it's probably better for you to talk about this, but extensive knowledge on the chemical resistance of PEEK to a whole range of oil field chemicals, and so we can answer more specific questions if you have them on more specific chemicals as required.
Great, thank you for that. How about this one? So, is there any elaboration on metal connectors?
Sorry, I'm not sure I quite understand the question.
So they're looking for us to talk a little bit more about metal connectors within the overall environment.
Okay. So our end fittings are made up of metallic components. Clearly, there are compatibility issues between metals and composites. But this is dealt with in the design. So there are the end fittings are metallics. The interface between the composite and metallic is dealt with in the design, and the metallic interface allows us basically to terminate the pipe in any way that's necessary to interface with existing or new design connection interfaces.
Okay, thank you very much for that. Let's put a few more of these questions in. What is the resistance of PEEK to sour gas?
I'll happily take that one. PEEK is exceptional in H2S. It's probably one of the best polymers out there, both in terms of retention of properties and resistance to permeation. So, as Mick said a few moments ago, we've very extensive test data, testing to standards like ISO 23936 and NORSOC M710, and we've done a whole gambit really of H2S contents in the gas fraction of a three-phase mixture. So we've done 2%, 10%, 20%, and in fact we've even done a series of tests at 100% H2S in the gas fraction. And actually what that told us is that so long as we're below 200 degrees Celsius, we're not going to have any serious degradation issues in meaningful time scales, and by that I mean in looking at many years of service life.
Brilliant. Thank you very much for that response. And I think we may have to wrap up with perhaps just one more question. Otherwise, we could probably go all day with the amount of great questions we've had. Do we have a field today where the technology is being deployed, and what are the kind of initial key learnings from that?
Sorry, is that could you just repeat the question?
Sorry, yes. Do we have a field today where the technology has been deployed, and what were the initial kind of key learnings from that deployment?
Yeah. So we have a deployment in the North Sea, and we have an imminent subsea deployment in the Caspian Sea. We have other deployments topside as well. And what we've been doing is working with the customers to monitor performance and, where possible, taking the product back to factory to do testing and inspection. And all performance we've seen to date is exactly as expected. We've had no issues, and the product performs well.
Fantastic. Well, thank you very much. Thank you very much for that, and thanks to all of you for getting involved. As I say, apologies if we didn't manage to get around to your question today. There were many to get through. Shortly after the webinar, the team will do their best to get back to each of you individually to answer your queries. So thank you for your patience on that. I would also like to say thank you again to Mick and Jeff. Thank you to all for joining us. We hope you found the session today useful. We thank you for your valuable comments, questions, and polling responses. Please remember that the proceedings will be made available as soon as possible for all registrants, and details will be sent out shortly for access. If you have other queries about webinars or other services provided by Spinners and Bradford, please get in touch with me. Thank you again, and goodbye.